I'm Ffion Lightfoot. This is my Physics 2211 Lab 1 on constant velocity. So I will give you a brief introduction of my lab. I will show you the observational model I used, computational model, a comparison of these models, and the additional questions that I asked about this lab. Next, I will be going over the purposes of this lab and Newton's laws. The purpose of my lab was to review the main principles of Newton's laws of motion and apply these principles in real-life scenarios, for example, pushing a car on a straight track. I analysed the car's constant velocity and then I will compare the observational model to the computational model. Newton's first law is also known as the law of inertia, and it states that if a body A exerts a force on body B, then body B will exert an equal and opposite force on body A. Newton's second law is mainly known as an equation of force is equal to mass times acceleration with the units of newtons. But when there's no net force, that means that there is a constant velocity, which also means that the momentum is constant. So we then get the equation momentum equals mass times velocity. In our lab, there is no net force. There's also two formulas that we have learned in our Physics 2211 class. This is the velocity update formula, which is the final velocity equals the initial velocity plus the net force divided by the mass times delta t. And then we've also got the position update formula, which is our final position is equal to our initial position plus the average velocity times delta t, which we will use these two equations throughout this lab. For my observation model, I used the tracker video analysis website, which I was able to insert a video of my experiment, which was a mass sliding across a straight line with a constant velocity. From this, I was able to observe the object moving with this constant velocity, and the path that we used was frictionless. So we had to assume that friction was negligible and that the drag force was also negligible. This would mean that the net force was zero once the object was pushed. So from my analysis, I was able to get data for the initial position and my initial velocity. The way I did initial velocity was my average velocity, as since there is a constant force, velocity is constant. So my average velocity is also my initial and final velocity. You can see some of my data points on the left-hand side here, and I was able to calculate my initial position was minus 0.05, and my initial velocity was 0.2654 meters per second. Next was my computational model in Glow script, and I will go over the properties and conditions and the calculation loop analysis. So as shown on the slide, you can see that I have my position vector and my velocity vector of the mass that I was using. So I was able to insert these from the tracker and the previous calculations I had done. So this is the code that I was able to use to get a comparison graph. Here we have my calculation loop analysis, where we can see that the net force is 0 as the vector 0, 0, 0 is equal to 0 newtons. We also have my ball velocity, which shows that there is a constant velocity of 0, 0, 0, which also is where I use the equation, the position update equation. And then below that, circled in the pink box, I have my position update equation. In the graph below, the thicker dotted line is my observational model and the thinner is the computational model. As you can see, the computational model is perfectly linear and the velocity of the observational model begins to decrease as time decreases, which shows that there was a net force experienced. So finally, onto the questions. What if you flip the axes so that plus x and minus x axes were interchanged? This would result in the slope of both graphs becoming decreasing instead of increasing, but it wouldn't actually change the difference in the two graphs as the data points aren't changing. And for what does this mean? Can you identify how many forces were added to achieve zero net force? We can't actually do this as we're not fully aware of the push and pull forces, for example, so we can't estimate it, but we do know possible forces would be air resistance and friction. Thank you for listening to my lab.